Hello, I'm Bruce.
Hi, I'm Aditya.
We are the Risky Scientists. This is our main episode for the week, and we're actually going to talk about social media this week. But first, we have our first question from the audience, and I'm excited about this because this question came to me,
Huh?
but it's for Aditya. It's a physics question, and it's a question that made me laugh because it's a fun question. I'm not a physicist, but it was accessible enough for me to have an opinion on it, a sort of theoretical opinion without being a physicist. But I'm eager to hear what the real physicist is going to say about this. So really fun question. So Aditya, are you ready for this?
Not at all, but let's do it.
So this question comes from Jim in California. And he
Okay.
says, I'm reading the quote exactly as he wrote it. So he says, my question is about quantum entanglement. If two particles are entangled and spin is measured at one particle, then the spin of the other particle is instantly known. Now, Einstein's quote, spooky action at a distance. The distance between the particles can be small or it can be as big as the universe. It doesn't, I think he means it doesn't matter to the
Yeah.
law of the spin, the entanglement. If one particle was in a location of extreme gravity
Mm-hmm.
and the other was somewhere with lower gravity, to an observer, the entangled particle in the high gravity region would have a slower clock than the one in the lower gravity region. Does this mean cause and effect could be reversed by measuring the spin of the particle with the slower clock? Question mark. And then there's a follow-up here, and then there's actually going to be a second question. The effect of observing the spin of the slower clock particle would instantly tell the spin of the faster clock particle, but that instant of knowledge would already be in the past according to that particle's clock, this one. So wouldn't this be putting the effect of observing the slower clock particle, knowing the spin of the faster clock particle,
Mm.
before the cause? So would this be putting the effect of observing the slower clock particle before the cause, putting the effect before the cause? And he continues, I'm having a hard time wrapping my head around this. I think we both are. I want to simply say that all time is local and that cause and effect are unalterable, but I think that is the coward's way out. All right,
Ooh.
Aditya, over to you.
Well, that's a meaty one, and it's one that as a physicist I have to first come and say, well, he our questioner is combining the two things that I think many people out there in the physics world are trying to combine and have no idea how to combine, which is quantum mechanics and gravity. So he's gotten right into the thick of the unknown from the get-go. But if I was to think about it a little bit more, let's see. So it seems like we're asking a question about quantum entanglement, along with the time dilation that comes from relativity. In this case, we're talking about a general relativity sort of time dilation. But there's a few things that break here from the very beginning. First of all, the idea of action at a distance in the first place means that your information from one spin to another, whatever process it's mediated by, is going faster than the speed of light. And so already what we have said is that we can have cause and effect that being switched around. So I really like the addition of gravity, and I think it's certainly a mind bender when you say, well, okay, what are we going to do with this gravitational effect, and what is causing what? But I have two objections. The first objection is that when you talk about quantum entanglement over very long distances, already in this case, you're assuming that information can travel faster than the speed of light. And relativity tells you that if you can travel faster than the speed of light, there's no reason you can't go back in time. So I had a friend recently send me a message asking, is time travel possible? And I was like, yeah, absolutely. You just go faster than the speed of light. So it is, in that sense, possible. But
It's
the second,
wait, just to be clear, it's theoretically possible, but practically impossible.
it's theoretically, even that it is theoretically possible is I think very sketchy, because in a
Practically.
sense, if you think about the famous equation E equals mc squared, what you're saying, right, is that the energy is a function of the mass times the speed of light squared. And I don't really like thinking about it this way, but an intuitive way to think about it is the common, what if an immovable object meets an unstoppable force? And so in order to accelerate something up to the speed of light, basically you need infinite energy. And if you think about the amount of energy it takes to accelerate just this tiny little proton or neutron or electron in particle accelerators, I mean, we're talking about miles of cables and wires and the biggest magnetic fields we've seen on the Earth, just to accelerate something that weighs 10 to the minus 32 kilograms or 10 to the minus 31 kilograms. So to accelerate a clock, think about that. I mean, it'll probably take more energy than we have with any form of energy that we have. So the objection number one is that you really can't get faster than the speed of light. So there's something breaking there to begin with. But objection number two, I think, is more interesting to me, which I pose back as a question to our question.
You can't do that. No, you can't do that. You haven't answered his question yet. So this this is what I would say in a classroom. You cannot answer a question with a question, at least not yet, because you haven't answered the question, right?
So the answer is that sure, you can switch cause and effect, because you've already assumed that you can go faster than the speed of light. So within the premise of quantum entanglement is the idea that if you can break the speed of light, there's no reason not to switch cause and effect. And I would argue that the gravitational bit, while curious, is a distraction. But the question that I would like to pose, and then we can try and answer, is why do we suppose that the faster clock is the one doing the causing? So I think there's an assumption also built into this that one clock is causing the other clock, but causation goes both ways in quantum entanglement.
Yeah, well, explain why you assume the faster clock has the causation, because the way I read it was the slower clock is being slowed by a higher gravity field, so it is the cause of the change in the entangled particle, which is in in a lower gravity field.
Yeah. So we're saying that the one clock is being slowed down. So generally, if you have two quantum entangled particles, let's assume in the same gravitational field, if I do something to one, you're going to have a corresponding effect to the other. And that's the idea. So the idea behind quantum computers, for example, is I can bang a particle on the head, and another particle somewhere far away will bang in some sort of relationship that we know theoretically. And so I know what's going to happen if I can measure one. I know what happened somewhere else. I think what the question is saying is, okay, if I measure this, then I know what has happened to this other one. So the idea is that we're saying, I think it's not so much about switching cause and effect as much as it is about preceding the future. So we're saying, look, if I measure this one, then I'm going to say I know what happens to this one. But now I'm measuring this one, which has a slower clock, which means not as much time has gone by. So I'm measuring the historical behavior of this guy. And I think the point is that if you mess with this one now, you've changed history for this guy. So you're reaching back into history and you're changing it. And that sounds really weird. But anybody who's taken a basic intro to relativity course, the first question is, what if you could go back and, I don't know why, apparently physicists also like classics, because the first question that you invariably see is, what if you could go back and save Caesar? And sure, you can go back and save Caesar. You just have to go faster than the speed of light. So it may not be satisfying, but I'm going to argue that the question is answered in the premise that if you have quantum entanglement that allows information to travel faster than the speed of light, then there's no reason you can't change history. There's no reason you can't proceed.
Okay, I follow, but what about the inference in the question that if the slower clocked particle is influencing the faster clocked particle, at some point you've got to regard the influence as being in the past from the faster clocked particle's perspective. So should that not break the cause and effect, because you should not be able to influence something in real time if you're actually shifting into a different time?
Okay. That's interesting. I would argue that that's an invalid inference because when you have instantaneous information transfer, you don't have cause and effect. You just have events. And you have events that are simultaneous in time. But the notion that you have cause and effect is in itself, I think, suspect in the case of instantaneous information.
Okay.
That's rewritten right. All of history when you have a slower clock. Right. And all of this is to assume that those clocks are entangled in the first place. And whether you lose quantum...
You can't do that either. You can't do, because now you're changing the assumptions of the question, and that's not fair.
Well, under the assumptions of the question, then we are allowing faster than light.
Right. So let me give you my non-physicist's knee-jerk reaction to this. Was I thought if the two particles are changing they're shifting out of the same time, I would have assumed one way to escape this is just the entanglement breaks, so they no longer are entangled. Right. So, and I'm thinking as a non-physicist that's a way of escaping a paradox or something that is mind-bending at least. And I'm also thinking about how, it's like super dimension theory or any theory where if we change time and space, like if we were to go back in time and change something in our own world, we should create a whole new world in a whole new dimension as a way of escaping the paradox now of where I'm going back and changing the past, which should change my own future, and it's the future I've come from. So now we've got a paradox. So one way of escaping that paradox is to jump into a whole new world, and that's the world I've changed. There's different dimension. So in this case, can we not just say if the clocks are changing, can't we just break the entanglement?
Yeah, but I think I would pose that back to you and say that that's escaping the assumptions of the question as well.
Touche.
But I think what you were saying earlier is another escape, which is to say that there's this multiverse theory in which all the possibilities are accounted for, and what you're doing is you're not rewriting history; you're just changing the history that you travel.
You're creating a new world.
Exactly. I have personally I have issues with that because it feels like a cop-out to say that everything is possible, and therefore,
Well, are we starting to prove that everything in physics is a cop-out? Because there are so many contradictions and paradoxes, we'll just cop out and create some other new theory to correct the prior theory we're working with.
Well, I would push back on that. I think there's really one major contradiction in physics now, which is quantum mechanics and gravity. There are others, but that's the main one. And it turns out that that's a really hard contradiction. So if you look there and you look deep in that, I think we'll see lots of things. We'll talk about, you'll see multi-dimensions. That's one way of doing things. There's the string theorists out there who are trying to use string theory to resolve the paradox. There's lots of other approaches as well. But really, going back to what we've said on these episodes, theories are really good approximations. And in their respective domains, in their domain of things that are really small, quantum mechanics is phenomenal. It's the best thing that we know so far. And then mapping out the behavior of the universe at large, assuming we're not sending clocks around the space, it's really good as well. So the problem really happens is exactly as our questioner pointed out, that when you start to send tiny clocks into very large regions of space.
Fantastic. That was a lot of fun. I enjoyed that question. I enjoyed the answer to it, and I think we haven't exhausted the answer, so there may be some follow-up on that. So Jim, that's the answer to the question you asked. If you want to follow up, feel free. We'll try to have as much fun with the follow-up as we did with the first question. So thank you, Jim, for the question. We encourage the audience to send us questions. That's useful for us to get questions. So please do that. So thank you, Jim. Thank you, Aditya. That was a lot of fun.